that is a phase difference. All right. So in general, you have two components on the XY plane. So now let's try to set the set this well, if you have a slanting angle, zero slanting angle, then you're going to get an upright ellipse on the XY plane. Okay, and this is the condition that if you set this phase, if we go back to the slanting angle theta, right here, if you want to set this phase, this number to be equal to 0, okay, the easiest is that you set this to be plus minus the 90 degree. So this term goes away and theta becomes 0. Where did you put it? Oh. Alright, so when you have a 90 degree phase difference or minus 90 degree phase difference, then you end up having this slanting angle equal to 0. So you can put the ellipse onto the upright position. Okay. So this is how you change the sort of trajectory of the electric field trace out during the propagation of the light. Well, we can set more conditions, but before we set more conditions, let's try to understand how this plus sign and minus sign will change the sense of rotation. Okay, and so let's take a look at that. We put plus minus sign into this expression, and this is the real expression. Okay, the final state of the light in the experiment will be described by this real expression. But in mathematics, in your calculation, you end up having this plus minus sign before this I notation, before this imaginary unit. So if you want to take advantage of using I complex notation for doing analysis, then you need to be able to keep track of this I in your calculation. Okay. So let's try to understand how the tip of the electric field will rotate based on this real expression, and then make a connection of the sense of rotation to this I, the sign before this I. So this is the strategy. Okay, we try to understand how the tip of the electric field rotate from this real expression. Okay. And then make a connection of the plus minus sign to this plus minus sign here. All right, so let's do our arctangent calculation to get this rotation angle, alpha. By doing the arctangent of EY over EX, you end up having this expression. And this tip is going to rotate over time. So let's look into the time, the term relevant to time. So if you have, for example, if I have this minus sign, multiply with this minus sign, you get a plus sign. You get a positive value. A positive angle will be rotating along this direction. By definition, on this XY plane, the positive angle is going above this line, right? So if I adopt the notation of plus sign here, and I have plus sign here, I end up having minus sign here. But then, in terms of the temporal variable, minus, you have two minus, get you positive value. So this means that if I follow this plus negative notation, then this electric field is going to be rotating along the counterclockwise direction. It's going to go like this, because you end up having a net positive sign in front of this time. All right, so now that we know this electric field is going counterclockwise direction, then let's make a connection. Let's make a connection with this I. Well, apparently I adopted this plus sign in front of this I. So in the future, when you adopt I notation and having plus sign, then you understood that the rotation of the electric field is going to be along the counterclockwise direction. Okay, so this is how you make a connection between the sense of notation with the sign before this I. And so people start to develop languages. This is counterclockwise the propagation, but then people like to use right hand. Then you're going to see that if you point this thumb along the propagation direction of the light, then you'll be this forefinger is going to follow this. So people call this right-handed polarization. Okay, but some people like to do left and right. If I stand here and then it's rotating to the left, then some people call this left polarization. So this is the sort of quite confusing when people develop languages, right? Some people prefer one way for the definition, and then the other people prefer the other way to describe it. So I sort of label here that the counterclockwise polarization, rotation of the electric field, in your textbook is called left polarization. But in engineering textbook, it's called right-handed polarization. So keep this slide as your reference, so you don't get confused. But then let's go to this minus sign. This minus sign will give a minus sign before this I. And then this minus sign before this I will give this plus sign for this calculation. And if you have a plus sign here, then the angle is going to reduce over time because there's a minus sign in front of this. When the angle is reducing, then this tip is rotating to the clockwise direction. Okay. This minus sign means that the angle alpha is reducing. Okay. When this alpha is reducing, then you have the rotation like this. And don't forget, this clockwise rotation is associated with minus sign before this I, or phi is minus pi over 2. And again, well, some people say, hey, it's rotating to the right, to your right. So we call this right polarization. But then some people say that, hey, bring up your left finger, your left hand, and then do this rotation, then this is left-handed polarization. Okay, and mostly in engineering textbook, it's going to adopt this right-handed or left-handed polarization. In artist's book, including your textbook, it's called right polarization, left polarization, and right polarization. So this is something that you want to resolve before you read the textbook. All right, is there any question about this? Well, we can do the same thing by setting more constraint into the expression. Okay. Now let's set the two amplitude of the two components to be the same. Then you will end up having a circular polarization. But then if you use the Jones matrix, it's going to look like this. For this part of the slide, I adopt I. So I keep track of the optics textbook convention. So for plus I is left polarization. For minus I is right polarization. Okay. So this is how you write down the proper expression to reach some conclusions of the polarization state of light. All right. Any question about this? So far so good. Well, mathematics is a little bit abstract. But then if you play with the polarizer, then it could be more interesting. But later I'm going to show you some experiments. Okay. But this is the circular polarization. Well, you do the same thing. You calculate the arctangent. Okay, you calculate the arctangent to determine how this angle is going to change with time. And again, if you adopt this minus notation, if minus gives you plus notation, the angle is going to increase with time. So it's going to rotate to your left. And this is called left polarization. When you adopt this minus sign, you end up with this minus sign here, but you have plus sign here. Then you know that the angle is decreasing with time, so you're going to have right polarization associated with this minus sign. Okay, and this is the same as before, except that we specify that the EX, EY have the same amplitude, so it becomes circular polarized light. Okay. All right. So now let's talk about polarizer. For polarizer, last time you saw this, and I show you that if I put the polarizer here, in fact, the light coming off on this projector is being polarized, so that you can select different colors on this screen. Okay. And so think about you have a randomly polarized light in the back of this projector, and then if you put a polarizer in front of it, then the light coming out from this projector is going to be polarized. But then you can program, say, hey, green light, it has to have a polarization direction along this direction. So you can use a polarizer to select green light coming out from this projector. But for different lights, you could program it to have different kind of polarization direction. But in space, you only have two choices, right? Polarizer only have two choices. So you end up having seeing that the green light is fully polarized along some direction, and other lights are mixed along some directions. Okay, because you don't have the white light can be decomposed into red, green, and blue colors. But the choice from your polarizer only has two, either vertical or horizontal. Okay, so you need to do more optical signal processing to be able to project different light onto a screen. All right, so imagine that you have some backlight on your screen like this. In fact, you can also do this. If I show you, let me turn on really bright, and then you can. Okay, I make it bright on my screen, and then you put your polarizer on top of it. But then if you rotate it, could you see it? If I do it here, you'll see what happens. This is the polarizer in front of it. And then I start to rotate it. Ooh, wow, you see nothing. And so this, what happened? That's good, yeah. So let me do it again. You can see something, okay. You can see something from this. And then when you rotate it, ooh, wow. So this means that the light coming out from this screen is fully polarized. Okay, and so this means that the structure of this screen, right outside this screen, there's a polarizer on it. Because if we do polarization, I don't know how good you can see this, but this is also polarizer. Can you see my nose? I cannot see myself. I can see my nose under the line, and I put a polarizer here, and I rotate. This is a bad experiment. Anyway, if you have two polarizers, and they are aligned along the same direction, you can see a light. Can you see me a little bit behind this tube? Mm-hmm. Now I start to rotate this by 90 degrees. Ooh. No. It turns black, right? become black when I rotate this 90 degrees. So this is a polarizer, and we call this analyzer. Oops. Anyway, we call this analyzer because I'm analyzing the light coming out from this polarizer from your point of view. Okay. So this is all black, and then you can see something behind it, and then I rotate this 90 degrees, you see nothing. Okay. And the intensity detected by my eye varies with the angle of this guy. Right? Now you can more or less see me, and then if I turn this to vertical direction, you see a total darkness. So the intensity seen from my eye, basically, it is relevant to this rotating angle. All right, so you see something, and let's try to analyze it. Okay, try to set up this computer again. When I learn something, I always want to see real things, but not based on imagination. Now, too many virtual things, it's no fun. Okay, so let me go back in this configuration. You have a polarizer before a randomly polarized light. And then use an analyzer, rotate it with an angle to detect some light in your detector. So this is exactly the experiment we just did. Okay, and turn out that when this angle is aligned with this the axis of the polarizer, the transmission axis of the polarizer. So apparently there's a transmission axis of the polarizer. Okay, the transmission axis of the polarizer is that well, on this fin, we have polymer aligned like this. Okay, and array of polymer molecules aligned like this. Okay, there's a large area on this. When you have an electric field along this direction, along the same direction, along the direction of the train, when you have an electric field along this direction, what happens? Or what happens is that the electric field pull this chain of molecule. When the electric field pull the chain of the molecule, the molecule will absorb the light. So the light cannot go through with this polarization. Only the light will go through is that if you polarize light along this direction. And so this electric field cannot pull the polymer effectively, so this polarization can go through. And this is called transmission axis of a polarizer. Okay, so this is intuitively clear. Any problem with this? Eugene? One more time, okay. When you have a polymer is the long chain of molecules. Okay, and if you have a long chain of molecules, it's easy to pull it, right? And how would you pull it? By using electric field. Okay, by using electric field, you can pull it. When you pull it, you transfer energy to these molecules. So this means that your energy is absorbed by these molecules. So if you polarize the light along this direction, the light cannot go through. Okay. Stavirua, can you take this concept? Right? When you pull something, you need to spend your energy. Right? So if you polarize the light along this direction, the light cannot go through this polymer. It's just like a wall because it absorbs all the energy from you. But if you polarize the light along this direction, well, the molecules are not going to cooperate. Okay, it's relatively hard to pull molecule along this direction. So the light will just go through. There's no energy exchange. So this is how a polarizer is made. It consists of long chains of the polymer molecules. So there's a transmission axis for this polarizer. So if you put the transmission axis of the analyzer along with the polarization direction of the light will just go through and give you the maximum intensity when theta is equal to 0. When this theta is equal to 0, you get maximum intensity. But when you rotate this by 90 degrees, well, the transmission axis is along this direction, but then you polarize your light along this direction. This means that you will be blocking the light, okay? And then you set this to 90 degrees to get 0 intensity at the output. Okay, so this is similar to that. If I have the polarizer like this, and then I rotate this to 90 degrees, you see nothing. Okay, you just see all black of the darkness, because the polarization of the direction of the light and the transmission axis of the polarizer are perpendicular to each other. Okay, and we call this Morse law, and we'll derive this in a moment by using Jones matrix. Okay, but this is sort of a little bit tutorial for you, and we'll be deriving this in a moment. Okay, Shukai, any question about this?
I think it's a bit complicated, so
It's confusing?
not quite confusing, but I think maybe I should think it again.
Okay, let me do experiment in front of you. You have a screen, and then you see oops. Okay, then let's rotate it. It needs to be seen from your eye, from your vision. This is the okay, OLED is circular polarized, so it's not so easy to do. Your screen is the immense.
polarized.
Oh, okay. Okay, this is the all dark, right? So and so this means that you have some transmission axis. Okay. All right. So then we continue to rotate, and it becomes dark. So this means that there's some transmission axis for this guy. Okay. So I'm talking about the transmission axis for this guy. And so if this light coming out is already polarized like this, the transmission axis, if the transmission axis is also along the same direction, you see brightness. If the transmission axis is like this, then you cut all the light. Okay, so you rotate it, and then you identify that when the two axes are perpendicular to each other, then you see nothing. Okay. Well, so OLED is the circular polarized light, so it's different. So it's good that you can see some optical phenomena in your eye, and then make a connection to the calculations. But then we spend a lot of time, and I doubt seriously that we'll have time to go to the cafe. Anyway, all right. So we understood that if you want to manipulate the polarization state of the light, we need to be able to control the amplitude and also the phase. Okay. So imagine that you have some sort of optical elements that can control the amplitude of and also the phase. Then you'll be able to manipulate the polarization state of the light. So it's very nice that you have the liquid crystal kind of screen, and also you have organic liquid crystal organic OLED kind of screen that you can sort of put information into the polarization state of the light and then analyze it by using your eyes. Okay, but think about that. If you have some sort of so-called wet plate that is able to change the phase of this, then you can do polarization state conversion. Okay, and then of course you want to decompose the input into X component and Y component first, right? And then for the X component and Y component, imagine that the acquired phase are different. For the S component, you have the propagation of constant of Kx propagating along this Z direction for a thickness of D. So turn out that you have this term in your calculation. So remember that you have cosine kz minus omega t kind of expression, and the phase accumulation comes from this term. If you have some spatial thickness in space, right? So if you have the thickness of d, then you'll be calculating this phase. Okay, and so we are doing this calculation right here. And this k, remember this is 2 pi over lambda. So you end up accumulating the phase for this X polarization for this much. And the same thing along Y direction, you can accumulate a phase this much. Okay, and suppose that this Nx and Y are different. Or in some materials, yes, we have done experiment before, right? This is a calcite crystal you played with last week, and for different polarization of the light going to this crystal, the reflecting that's seen by the light will be different. So Nx and Y can be different, and we call this birefringence of a material. We've been talking about this, okay? But then you see that when you acquire different amount of phase along X direction and Y direction, you have a phase difference. You have a phase difference that will allow you to